A pleasant day to each and everyone. My name is John Carlos C. Julianda from BS Geological Engineering 2201, and I am here to present a research paper entitled Electrical Conductivity Profiling for Rapid Contamination Assessment in Unsaturated Zone, a case study of an MSW landfill. The content of our study contains the introduction, literature review, objectives, site description, methodology, result and discussion, and also the conclusion. In recent years, stricter environmental and health policies have made contamination assessment at old polluted site increasingly important. It is according to Mukherjee et al. Of 2015. In situ techniques are especially valuable as they provide fast, on site data, avoiding delays linked to lab based analysis. One promising method is measuring soil pore water electrical conductivity, or the ECPW, which reflects contamination levels. ECPW increases with dissolved organic substances, which is common in landfill leachate with high total dissolved solids or TDS. Some contaminants are retained in soil while others stay in their pore water, affecting ECPW depth profiles. However, direct ECPW measurement in unsaturated soil is difficult, especially at depth, due to limited sampling tools. As an alternative, bulk soil conductivity or the EC bulk can be measured using probes or time domain reflectometry or TDR. EC bulk reflects the combined conductivity of soil solids, air, and pore water and can be used to estimate ECPW indirectly. The earliest model linking bulk cell conductivity or EC bulk and pore water conductivity or the ECPW was developed by Archie in 1942, using a power law equation originally for sandstone and later applied to soil. This relationship incorporates factors like porosity, water content, and saturation, but is valid mainly for non-conductive soil with sufficient moisture. Soil mineralogy greatly affects EC bulk, with clays showing higher conductivity due to surface effects. However, this influence weakens when ECPW is high. Porosity also plays a role, but its impact varies with the level of pore water conductivity. Among all, volumetric water content is the most critical, as EC bulk depends on the water volume and not in the mass. Electrical conductivity methods, including the use of resistivity piezo cones, have been effectively used to detect contamination and infer soil properties such as porosity and tortuosity. However, most research has been lab based, so often under simplified conditions. Field validation remains limited, especially in complex sites like landfills where soils and contaminant profiles are highly variable. For the objectives, this study aimed to validate the use of bulk soil conductivity as an indicator of leachate migration in the unsaturated zone beneath a non-engineered municipal solid waste landfill. It also assessed the correlation between the bulk soil conductivity, pore water conductivity, volumetric water content, and surface conductivity to understand their interrelationship. One of the objectives was also to evaluate the contribution of macroions in the leachate to the electrical conductivity of pore water, understanding how they influence conductivity measurements. Lastly, the finding of the study aimed to improve environmental monitoring strategies for old landfills, particularly in unsaturated zones, and support dynamic remediation planning using the triad approach recommended by the US EPA. For our site description, the study was conducted at a non-engineered municipal solid waste landfill in Baswa village, North Delhi, India, located at the intersection of the Indo-Gangetic Plain and the Delhi Ridge with alluvial soil over quartzite bedrock. The subsurface features a high permeability alluvial layer of 10 raised to negative 5 meter per second, with groundwater flowing eastward toward the Yamuna River and fluctuating seasonally. A drastic analysis identified the site as highly vulnerable to groundwater contamination due to shallow water tables and permeable soils. Additional pollution sources include an unlined drain carrying sewage and industrial waste, leachate ponding on landfill's north side, and soil-like material deposits on the south side from waste mining. These conditions persist even after landfill closures, acting as a secondary contamination sources. The landfill is adjacent to densely populated residential areas where health risks have been reported by local residents. For the methodology, the study was conducted between February and April 2023 at the Baswa landfill in Delhi, India. 7 locations were selected around the landfill to assess contamination based on the proximity to various contamination sources. These locations were categorized into 4 groups: the waste overlying soil, ponded leachate overlying soil, and soil like material overlying soil, and also MSW waste. In here, we use field investigation tools such as number one, the piezo cone penetration test or CPT. It is used for subsurface soil characterization. The piezo cone measured the cone tip resistance and friction to classify the soil based on the soil behavior index or LC and also its pressure. Number two, we have hydraulic profiling tool or HPT, which was used to measure bulk electrical conductivity and estimate the saturated permeability. Lastly, we have the soil core sampling, which is conducted using a dual tube sampler. This method ensured high quality, cross contamination free samples. Soil samples was subdivided into 15 centimeter sections for water content analysis, and pore water was extracted using a centrifuge system for further conductivity testing. During the laboratory analysis, pore water samples were analyzed for electrical conductivity using an EC meter and for cation concentration using inductively coupled plasma mass spectroscopy or ICP-MS. An ion and ammonium concentration were determined through ion chromatography. Standard geotechnical tests were performed on soil samples, and mineralogical composition was analyzed using an X-ray diffraction or XRD. For our resultant discussion, first one we have the site characterization. The subsurface of the landfill mainly consists of poorly graded sand with intermittent layers of clay and silty sand, shows low permeability. CPT and HPT tests revealed significant heterogeneity, and empirical correlation confirmed the permeability and soil type classification. For leachate sampling, a sharp increase in EC bulk below 9.5-meter depth indicated the presence of a saturated leachate zone, suggesting mound formation. The leachate's composition was consistent across location, and lower permeability at greater depth implied waste consolidation. For our composition of pore water in leachate, pore water was rich in major ions, with heavy metals found in the trace amounts. Variation in the ion concentration between sections were attributed to factors like ponded leachate and differences in waste type, like MSW versus the SLM. For the electrical conductivity profile, a significant drop in ECPW was observed in clay layers, pointing to contaminant attenuation through sorption and chemical reaction, which is in contrast, sand layers showed little change in ECPW, reflecting unimpeded contamination migration. For the impacts of clay on bulk cell conductivity, surface conductivity from clays was found to be negligible in high ECPW conditions, contributing less than zero point 0.5 ms per cm to EC bulk. Normalized EC bulk analysis further confirmed that clay had minimal impact on bulk conductivity at the landfill. For the correlation of bulk and pore water conductivity with water content, a linear relationship was observed between EC bulk and ECPW and also the volumetric water content, valid above a threshold of 5% moisture. Below this critical content, EC bulk approached zero despite high ECPW, indicating disruptive conductive pathways. For the contribution of ions to pore water conductivity, attenuation of ions like potassium, ammonium, and hydrochloride in clay layers demonstrated strong sorption behavior, while inert ions like chlorine showed little to no reduction. A strong linear correlation between ionic strength and ECPW, which has a value of 0.81, indicated that macroion concentration primarily governed pore water conductivity. Lastly, for our conclusion, the field study conducted at a 30-year-old non-engineered municipal solid waste landfill demonstrated the potential of using bulk soil electrical conductivity or EC bulk to evaluate contaminant migration in the unsaturated zone. a moderate linear correlation of 0.46 was observed between easy bulk and pore water conductivity, especially when volumetric water content was considered. Surface conductivity from clay was found to be minimal, contributing less than zero point 0.5 ms per cm, largely due to the ECPW values of 5 to 15 ms per cm at the site. However, the correlation between EC bulk and ECPW breaks down below a critical water content of approximately 5%, as inefficient moisture result in discontinuous pore water channels that inhibit central conduction, causing EC bulk to approach zero. The dominant contributors to ECPW were macroions such as sodium, potassium, ammonium, calcium, magnesium, chloride, sulfate, and bicarbonate, which shows a strong correlation of 0.81 with ionic strength. Heavy metals found in trace concentration had minimal influence in conductivity. This finding suggests that easy profiling can serve as a rapid, semiconductive method for identifying contamination zone and guiding remediation strategies. However, limitations due to low moisture levels highlight the need for additional research to define reliable water content threshold. Given the absence of standardized guidelines for using easy bulk in soil contamination assessment, this study introduces a novel framework that combines CPTU for classification of soil and HPT for permeability, and also the EC measurement, which is for the electrical conductivity. Future work should focus on validating this approach across various contaminated sites and exploring alternative tools like time domain reflectometry or TDR to enhance the reliability and comprehensiveness of contamination assessment. And that is the end of my presentation. Again, I am Joan Carlos C. Julianda from BS Geolang 2201, and this is the final presentation to the principles of geophysics. Thank you for watching.